and today's lecture will be physics on the Bethe lattice. And we will try to cover the electronic structure today. If I feel inspired and you feel interested, then we will also do the magnetic, the Ising model on the Bethe lattice. So let us do the electronic structure, but first I have to tell you what a Bethe lattice is. The Bethe lattice was invented by Hans Bethe, of course. I mean, it goes by his name, Hans Bethe. I think 1935. I put a small question mark around there. Okay, and it's a very delightful construction. It's something that you enjoy looking at and doing physics on, but it is not something that is very, very, how should I say? You might feel that it's not very pertinent. But pertinent or not, because it is so enjoyable, we should do it. Okay, and it is supposed to be a model for a disordered system. Okay. So, as you all know, if you have even the simplest interacting system, like the Ising model, or like the Hubbard model, or even transfer Hamiltonian, we cannot solve it exactly because unless you go to a very special dimension like one dimension. Say the Ising model is exactly solvable in one dimension, but not so, say, in three. Okay. So what Bethe did is, he said instead of changing the Hamiltonian, so you can tweak the Hamiltonian, okay, and you can solve it exactly by saying having a spherical model instead of the Ising model. But you can do something else, he said. You can tweak the lattice. You change the lattice so that you can get an exact solution. So he tweaked the lattice and created this lattice, created the system, and created a system which is dendritic and has no closed loops. It is dendritic. So how does it look? So, for example, I can only take part of the board here because I don't want to erase this picture. You start from a point. Let's call it a lattice point. Okay. Let me call it 0. And say it has 3 nearest neighbors. So Z, which is an index for nearest neighbors, is 3. Okay. So you have 1, you have 2, you have 3. Right. This is called the first generation. So let me call all of them as 1. So it's connected 3 ways. Now this one, okay, this point, okay, it is also connected 3 ways. Okay. So this is the second generation. Okay. Then you continue. Okay. This is also connected 3 ways. 1, 2, 3, third generation. But notice what I'm doing. I'm not connecting this to this. Is that clear? So there is no closed loop. And I'm now going to run out of space, so I won't even try further. Okay. Similarly, over here, on the top side, I can keep branching. So it's like a tree structure, and the tree structure keeps branching, such that 2 branches don't meet. Okay. So this is called the Z equal to 3 Bethe lattice. Now, is this clear? Aparna?
Yes, sir.
Thank you. So it is clear to you as to what is going on in this Bethe lattice. Okay. So now let us say how do you count the number of atoms, say, in the nth generation, or the number of lattice points in the nth generation? So let us take this number n, and let small n stand for the number of generations. Okay. So this is equal to 1, because this is 1, this is 1. In the next generation, it is z, because z is equal to 3 here, so there is 3 over here. In the next generation, you have z into z minus 1, that is in the second generation. Okay. Right? You don't count the one before, so that's why you have z minus 1. In the generation after that, you have z into z minus 1 the whole square. And similarly, in the nth generation, you have z minus 1 to the power n minus 1. So that is first generation, where n is equal to small n is 1, minus 1 is 0. Second generation, z minus 1 to the power 2 minus 1. Third generation, z 3 minus 1. Nth generation, n minus 1. I can sum the series. Okay. If I sum the series, this is equal to 1 plus, now let us see, z, right, plus z into 1 minus z minus 1 to the power n over 1 minus z minus 1. Because it's a geometric series, I can sum it up. Is that clear?
Yes, sir.
Okay. So basically, I'm using the geometric series summation and I get this. I can simplify this. Were I to simplify this, let me write down the result and you can work it out. Okay. For yourself, the result is simply z into z minus 1 to the power n minus 2 over z minus 2. I haven't worked this out, but I can assure you that if you do work it out, you'll get this result. That is the number of atoms or lattice points in the end up to the nth generation. How many surface atoms? Okay. Supposing I denote my S of n as the number of atoms on the surface. Okay. So this is simply, I would say, how much? This particularly is the last count, z into z minus 1 to the power n minus 1. That's just the last entry over here for this first line. So, if I were to take the ratio of the surface atoms to the total number of atoms, Sn over n to the power n, I take this, I divide it by all of this. Correct? So, if I do that, and let me write down the result because you can all work it out. And if you're not happy about it, you can let me know. Okay. Okay. Since I don't have it here, I better work this out, or I better take this from somewhere and I work it out in my earlier. So let me just work it. Let me just give it to you. It will simply, I should have known this, z minus 2 over z. I think you can see what I'm getting at. Okay. I have the total number of atoms up to the nth generation, cleanly worked out. Okay. By how? By arithmetic progression. I'm sorry, geometric progression. I have the total number of atoms on the surface. There's no doubt about this. I divide the two surface to volume ratio, so to say, and I get this answer. That is what it basically tells you, that this is a finite number. There is a very large number of atoms on the surface. Okay. Say for z equal to 3, if you this is an asymptotic result. This is an asymptotic result for n going to infinity. Okay, when you go to the infinite generation or say 100 generations down. Okay. And the asymptotic result tells you that the surface to volume ratio is 3 minus 2, which is 1, or by 2 is half in this case. How is it, say, for a three-dimensional lattice? For a three-dimensional lattice, Xn over Nn is equal to n to the power of 2/3. That is 2/3 of the atoms are on the surface. It's 4 pi r squared by 4 pi by 3 r cubed. So this goes as n to the power minus 1 by 3. When n becomes large, this goes to 0. For a general dimensionality, goes as minus 1 by 3. So unless you are in infinite dimension, this term is actually quite large. 3 dimensions. For n going to Avogadro number, it's a huge number. In 2 dimensions also, it is quite large, so on. Okay. So what it is essentially telling you is that the Bethe lattice is a very special lattice. It resides in infinite dimensional space. Why? Because as you can see very quickly that if I were to do this in 2 dimensions, there will be overcrowding right away. So it has to go to the 3rd dimension to avoid that overcrowding and touching each other and avoiding that closed loop. And if you go to, so it goes to the 3rd dimension, then it goes to the 4th dimension, and it goes into an infinite dimension. And they say therefore that the Bethe lattice resides in on an infinite dimensional space. And you can see it also over here that when D is very large, it's only in that case that Sn by Nn has a finite number. Like this. So that is so much for the Bethe lattice and the geometry of the Bethe lattice. However, I have to stress that the Bethe lattice has a slightly, if I might put it, it has a slightly it has a somewhat schizophrenic character. It sits in infinite dimension. It has an infinite dimensional character, but it also has a one-dimensional character. You might say, why is that? That is because the Bethe lattice is simply connected. Okay, so it is like in one dimension, there is no closed loop. In 2 dimensions there is for a square lattice or honeycomb lattice, but in 1 dimension there are no closed loops, and that is what the Bethe lattice is. So it has both characters. It has the simplicity of 1 dimension, so you can work out a many-body problem exactly, and it also has this infinite dimensional character. Right? So it is somewhat enigmatic. It is schizophrenic. That's what you would say. Since I am on the topic of lattices, I'll make a side remark and then proceed. That is, there are other lattices that people have invented. There is something called the Kagome lattice. There's something called the Husumi cactus. Those lattices, for example, look like this.
So,
yes.
before you erase it, the expression for n and n, that doesn't seem right.
This one?
Yeah.
This doesn't seem right?
Yeah.
Why is that?
Because in the second step, let's say we put z equals to 1.
Yeah, and that you don't do. Don't put z equal to 1. It doesn't work for z equal to 1. No. Yes, you don't. If you take that limit, yes. Okay. Because for anything, take from 3 onwards.
3 onwards, yes.
Okay, this blows up also. This also blows up. You can see that here. Okay. Agreed. Okay, I should have made that qualifier. You use this expression for the case Z3 or higher. Okay. So the number of connectivity, the connectivity of the lattice is 3. It can be 4 if you want, and so on. Good point. So let me erase this and continue with something. I just mentioned in passing that there are other lattices people have invented, and just draw one of them for you. Oh, I can't. I erased something that was very important. I just can't afford to erase this. So this was what here? 1. This was 1. This was 0. This was 1, and this was 2, right? Should I?
2 is just 2 times.
Huh?
2 will be just 2 times.
1.
You just have 2 branches.
1 is there, this is 2.
You are making 4 branches this time.
Why am I making 4? Yes. So this is 1, so this is 2. Sorry, this is 2. And now there is something 3. Okay. Yes, that's correct. Okay. So some of these other lattices called either Kusumi, cactus, Kagome lattice, for some reason associated with Japanese mathematicians and physicists, might look like this. There's a closed loop, okay, but it has only one connectivity. That is to say, if I have a triangle, this triangle is linked to this triangle, it is linked to this triangle, okay, but no two vertices are equal. That is, only one vertex of this triangle and one vertex of this triangle are connected. If this one were also connected, then this edge would get connected. Okay. So it has this kind of structure. Okay. So it is basically, apparently, the physics works out and can be done quite easily on these Kusumi cactus and Kagome lattice. You can look it up. I don't want to get into it. Our cup is quite full today with just the Bethe Lattice. So then the next thing you might say, what is the motivation? And I've already told you that you can solve exactly I should say solve some many-body Hamiltonians exactly. But there is something else I need to tell you, that there is a very important piece of work which was done in 1971. And basically, an important piece of work in the sense that it was for semiconductors, and it did the following. Okay. Amorphous semiconductors are disordered structures. Like there's, just as I said, for liquids, there's something called amorphous semiconductors. They were discovered around 1969. They could be doped. Because they could be doped, people thought that they can now be used for some kind of technology. But the point was, people thought semiconductor has a gap of 1 eV. It has a 1 eV gap. If you have it amorphous, then the whole thing will get so disordered that there will be no gap. Okay. So there is a semiconductor which has a gap. Okay. And this is the conduction band, this is the valence band, and this is say approximately 1 eV. Okay. That is for a regular crystalline semiconductor. If I have defects in the semiconductor, then there are levels in the gap. And certainly if you have something as amorphous and disordered as an amorphous semiconductor, then this gap would just vanish. If the gap vanishes, then you have something, either you get a metal or you get a mortar insulator or an Anderson insulator, but it will become either insulating or it becomes something else. You just can't do technology with it. And amorphous semiconductors are cheap to make. They are simple. Okay, they don't cost too much. Crystalline semiconductors are very expensive. Pure crystalline semiconductors that go into your, how should I put it, to this smartphone or something, is quite expensive to make. Very energy intensive. Okay. The amorphous one is cheap. Why don't we make it? But the issue is, does it have a gap? And there were two physicists who did solve a multi-band problem, an amorphous semiconductor problem on the Bethe lattice, and demonstrated that there is a gap. So they demonstrated. Yeah. Question mark on, is there a gap? And the answer is yes. Okay, and it was shown by two physicists, Vijay and Thorpe. Dennis Weir and Michael Thorpe, 1971, by solving. On the Bethe Lattice, on the z equal to 4. Why 4? Because the more semiconductors are 4-fold coordinated. So it is related to disordered systems. In fact, a large body of work exists which tries to demonstrate certain properties of disordered systems by simply cheating, if you would like to say, and doing the physics on the Bethe lattice. So the program today is, why don't we also try to do a simple problem on the Bethe lattice, say of the electronic structure? And that is what we will take up. But before I get out of it, I should pause and ask if there's a question. Yes?
Sir, I'm Chandrasekhar.
Yes.
Sir, so you said Z equal to 4 Bethe lattice, but then that would mean each atom is connected to 5, right?
Should I
So
say 3?
yeah.
Yes.
Okay.
Yes, that equal to 3 if you want. In this notation. Yes.
Yeah.
Correct. So each one is.
So they proved that even in a amorphous semiconductor, there's a band gap which is present by using the.
Yes, what they said is if you solve this problem, okay, you will still get a gap. And a good one.
Okay.
Good size one. Yeah.
Okay, sir.
Okay. So it became like a demonstration. Yes, even in a disordered semiconductor, you would have a gap. Something that you didn't expect. 71. Any other question? Okay, so let me continue. By the way, this will be one of the projects that I'm going to propose. Oh. Did all of you get the home assignment 3? Aparna, did you get it?
Yes, sir.
Okay.
So,
Yes.
regarding the home assignment, I think you sent it to the previous solid state physics group. So, like
Did I?
you have, yes, I think so. So, you have missed out Pratyush Patnagar, Krishna, and Sukant.
So could you send it to them?
Yes, I'll send it to them.
Send me a test mail with these names. You have sent me a test mail with the old names. Mr.
No,
Johnson.
I've sent both of them to you.
So
I
this
think
one
you accidentally sent to the whole account.
please send it again. Say test
Yes.
mail. Test mails. Say students P801. That should be the subject.
Yes.
Students P80. You have not sent it. So now it's your job to send it to the other 2 students. And your job to tell those students that they don't have to do this. By the way, we might have a test second exam next week or something. Okay. And that exam will serve, well, I'll talk about it later. Electronic structure. Electronics, right? Okay. So let us take the simplest Hamiltonian, single band, nearest neighbor. Let's take the on-site term to be 0. So I have a Hamiltonian. It is simply T. I will not put a minus sign because then I get confused with the sign. I not equal to J, nearest neighbor, I. As simple as that. Right? I not equal to j means if I'm looking at this side, then these are the three neighbors. I'm not looking at any further neighbors. So I have the Green's function g of e. I'm not using z because that will get confused with the index z over there. G of e is equal to 1 over e minus h. Okay. So be very clear, these are operators. So with E, there's a term called the identity matrix. So I'm leaving that out. I write this as 1 over E into 1 minus H by E inverse, which I will now write as 1 over E into 1 plus H by E plus scalar expansion, please. Okay. Therefore, I bring this E over to the left-hand side. I have E times G of E is equal to identity, I guess. There is an identity. Plus 1 over E into 1 plus H by E. Correct? Let's do that again. Let us see. E. Sorry. Let me just correct myself for a minute. Okay. Thus, I take this E out there, so I get a 1 plus H by E into 1 plus H by E, the whole square, plus H by E, the whole square, and so on. Are you with me up to this point? So this is equal to identity plus Hamiltonian, and the rest of it is again the Green's function, g of it. I pause for a minute so that you can take this down and you can be convinced that this is correct. Right? Right. So now allow me to continue. If you are comfortable with this expression, what I do is I take the diagonal matrix element of the Green's function, okay, say at the site 0. This being a Bethe lattice, there is another property that is obvious from this. It is self-similar in the sense that every point is equivalent to every other point. Okay. So I take the diagonal, whether I take the diagonal elements between 0 and 0 or between 3 and 3, it doesn't matter. It should be the same. So, long back in 1935, this property of self-similarity was known to physicists. It was rediscovered and made a big hullabaloo about when they had fractals, okay, which are also self-similar, but of a different kind, of a different genre. So let us take the matrix element of this, both sides, with respect to the Wannier states at 0, 0. So I have E times G, 0, 0. Okay. Let me drop this E. Of course, there is a function of E. Then you have 0, 0 will give you a 1. Okay. Because the Wannier states are orthonormal. Plus over here, you notice this is T. Right? We'll have a T. Right? On the left hand side, you have a 0. Okay, but then for H, the others cannot be 0. Okay, it has to be 1. And how many such 1s are there? Yes, who is the next student? How many such 1s are there? Akshat, yeah. How many are such 1s? 3. 3 of them. So I just have 3 T G 1 0. Okay. Because this is 0. Okay, on this side we have a 0. Okay, but the nearest neighbor has to be something else. That's what. It is 1. But there are 3 of them. That means to get this diagonal Green's function, I must know this off-diagonal Green's function. So let's worry about that off-diagonal Green's function. Okay, the off-diagonal Green's function, again I use this equation to say that it is E G 1 0. Okay, 1 0 What will the first term become? Yeah, Mr. Chandrasekhar, what is the first term?
So I couldn't hear. Could you repeat again?
I'll repeat it again. I am taking the matrix element of this equation now between 1 and 0.
So it will be
One.
0.
It will be 0 from orthogonality. So this term goes to 0. What about this term? Okay. I have to be a little careful about this term. This term will become T G 0 0 plus 2 T G. Let us see 2 0. Why is that? Because when you look at this term, there's one over here, one neighbor is right here, and there are two such neighbors. Right? So let us clean this up a little bit. This is what I will get. Let me rewrite this for you. And if you have a doubt, please stop me. We can go over this. Which means that I need to know what is G20. So E G20. Again, I use this my defining equation, which I am pointing out. It's equation 1. E20. What will the first term become? Yes, Saloni. What will the first term become?
So 0.
0. That is 0. That's not. What about the next term? I have to be at 2, no? So there is one which is right here, 1, and there are two of them which is 3. Okay. So I have T G G 1 0 plus 2T G 3 0. Clear? It's like it works out quite easily, and I can write the nth term. Can I or can I not? Okay. It's not too difficult to say. See that the nth term would be G n 0 is equal to T G n minus 1 0 plus 2T G n plus 1 0. At this point, I pause so that you can think that what I've done is correct. Now I suggest that G n plus 1 0 by G n 0, let it be put of quantity alpha. Okay, this alpha can depend on Z, or by the way, this Z, but Z is already, I've decided that I'm going to do it for Z equal to 3 Bethe Lattice, which I did not specify, but I should say it here, Z is equal to 3. Okay. So it will depend on T, of course. It will depend on T, and it will depend on E. If I do that, look at this term. What will it become? Supposing I divide by Gn minus 1 over here. Okay. So Gn0 by Gn minus 1 0 would be equal to alpha. Okay. So you get E alpha. Here you get T. Plus over here you have 2T divided by Gn minus 1 0. Right? I'm dividing throughout by Gn minus 1 0. So I can certainly write it as n plus 1 by n into n by n plus 1, n minus 1. So I simply get 2T alpha squared. So I divide all sides of all terms of this equation by the Green's function at n minus 1. I simply get alpha over here. I get alpha square over here. I can solve for alpha. It's a quadratic equation. Okay. So if I were to solve for alpha, what would I get? Alpha is what? Do that. I take this from this side in case you are more comfortable with this, something like this. Okay. And I decide to solve it, so I simply get E plus minus square root of, or let us say E square plus, sorry, minus ht square root by if you are with me, then what is it that we want? Why are we doing this? We are doing this to first understand the basic physics of the electronic structure of the Bethe lattice, taking the simplest Hamiltonian possible, the single band tight binding model, okay, with diagonal term equal to 0, with near stable interaction, which is T. Okay. We have taken Z to be equal to 3. And what are we after? We want to know the density of states. How will the density of states know? So let me ask you a quick question. Supposing you are doing a one-dimensional problem, okay? If we're doing a one-dimensional problem, the density of states should extend up to which point? From where to where? For a lattice like this. For this Hamiltonian, the density of states you would say will go from 2t to minus 2t. Is that clear? You would agree with that because we have this expression, we have done it many times over, the density of states goes from 2t to minus 2. So I want to know what the band edges would look like, how the density of states would look like. So you look for the density of states. In this case, since z is equal to 3, you would be interested in seeing how the density of states extends up to plus 3t and minus 3t. Okay, 6t. So, the answer is right here. The density of states will only extend up to square root of 8t. But we'll see how we get to it. So, but to get the density of states, what do I need? What is that one quantity I need if I want the density of states? Yes, Mr. Rishabh Varma, what gives me the density of states?
So green function, imaginary part of green, -1 over IP.
Diagonal part, which is the imaginary part of the diagonal Green's function that I'm after. So, although I have this alpha, I just have to work a little bit harder, just one step to get this diagonal part of the Green's function. And I do it at one shot right here. I say that yes, I need this diagonal part of the Green's function. So G10 is nothing but G00 into alpha. Okay, by this algorithm, G10 by G00 is equal to alpha. Take the alpha on this side, take the G00 on this side, and I get the G00Z for T is equal to 1 by T minus T. Of course, this alpha is quite a beastly quantity like this. So, if I simplify this, and I would request you to do it, I don't think I have the patience to do it right now. If I were to do this, you simply get, why don't we work it out? Yeah. 4 into E minus 3 into E square minus 3 T. That's what. How do you get this? I get it because I put this over here. The T will cancel out. I get a 3 by 4. Okay. I take the 4 in the numerator. Okay. And what I would have here is the 4e minus 3e. Okay. So I'm left with a solitary e, and then I'm left with all of this. Is that clear? So, I pause for a minute so that you're convinced that what I've written down is correct. While you are thinking about the step, okay, let me erase the rest of the blackboard because I've gotten what I'm after. And all of this is now unnecessary.
Sir,
Yes.
there's a plus minus solution, right? So what about the other one?
Yeah, there's two of them, a minus plus.
Yeah.
They allow for both. Okay. Thirdly, what would happen is when you take the imaginary part, you must only take that part which gives you a positive a positive density of states. You can't take both sides, both sides. Okay. Density of states is equal to minus 1 over pi, the imaginary part of G00. So now I'm after the imaginary part. What will produce the imaginary part? Only if E is less than square root of 80. That will produce the imaginary part. So I will have to write this as minus 1 over pi, the imaginary part of, let us say, 4 over E. Let me keep both sides, but I'll only take one of them, as I said, 3 into I, 8t square minus E square, square root. That implies that E is less than square root of 80. Now, all that you have to do is something like this. If you have A minus IB or something, you write it as A plus IB over A square plus B square. Okay? And that's the imaginary part would be, if I'm looking for the imaginary part of this, it is simply B over A square. Keep both signs until the end and choose the one which will give you a positive semi-definite density of states. Once again, the answer is simple. I mean, you can work it out. You simply get 3 by 2 pi 8t square minus e square square root over 9t square minus e square. It's an interesting structure. It is quite clear that E will go only up to square root of 8 dt. So you have, if I were to plot this, I have 3t, I have minus 3t, but it will only go up to this point, square root of 8 times t, and this point is nothing but minus square root of 8 times t. Try plotting this. I'll give you a minute, a couple of minutes to see if you can plot. Okay. So have you done, or you want a couple of minutes more? Yeah, Aparna?
Sir, a couple of minutes.
Yes?
Sir, a few minutes more.
Can you plot, have you plotted this, or you need a few more minutes?
I need a few more minutes.
Okay. Have a few more. Meanwhile, I'll write the references for you. And a Cyril Dom in Advanced Physics. I think volume 9. This is for statistical mechanics. And for the semiconductor one, it is Michael Weir, Dennis Weir and Michael Thorpe. Physical review. D 1971. I'll give you the volume and I'll give you the page number also. The volume is 4 and page number is 351. Starting 1970, the physical review, which was only one of them, split into several. And the physical review B became the solid state or the condensed matter physical review. Okay, and you can see it is 70 because it comes every 6 months. The volume number changes, and so the volume number 1970 beginning is volume number 1. 70 second half, volume number 2, 71, this is the second half of 71, volume number 4. Just an interesting aside on how research has multiplied, and now there are thousands of journals, but the splitting which began at that time was 1970, physical review. There was a B version. Okay, the A version was atomic physics in general, I think, and the C was nuclear physics, and the D was particle physics, and so on. Okay. So if you have plotted it, fair enough, or you can try it out. I can tell you it looks like this. There is a hump on both sides. And if you don't believe it, you can think about it and try to plot it. Okay? So to cut the long story short, we have taken the simplest model and worked out the electronic structure on the Bethe lattice for the simple model. That is one. The second is, and so we have a certain comfort level, and basically the property that we have used is the self-similarity of the Bethe lattice. This side is the same as this side is the same as this, and the non-connectivity. The branches don't connect to each other. There are no closed loops. Okay, there's no looping here, unlike a two-dimensional lattice or a three-dimensional lattice. This first reference by Cyril Dome, Advances in Physics, I didn't give you the year. This year is 1960. The first page number to it. This is for statistical mechanics. In fact, Bethe invented this. Bethe lattice for statistical mechanics. Okay, and this reviews all the literature up to that point. Good reference. Okay. This is basically the electronic structure. It's not a reference. It's basically a demonstration that if you take the 4-band Hamiltonian, not a single band, 4-band Hamiltonian, and work out the Bethe lattice electronic structure for Z equal to 3, okay, 4-fold coordination, then you would get a band gap. They demonstrated it, and so the work became famous, at least for a while. Okay. Any questions? Okay. So I'll stop the recording because now this part is over. Good.